In this presentation, we have talked about thermodynamic potentials, the thermodynamic functions, internal energy, enthalpy, Helmholtz free energy, and Gibbs energy are called thermodynamic potentials since they behave similar to potential energy in mechanics. To maintain a stable equilibrium, the potential energy of a system always decreases. Here also, the thermodynamic functions behave similar to potential energy in mechanics. To maintain the stable equilibrium, the values of these thermodynamic functions decrease identically with the potential energy in mechanics. Therefore, these thermodynamic functions are called thermodynamic potentials. Now we have to discuss them one by one. The first function is internal energy. Internal energy is represented by the letter U. According to first law of thermodynamics, the quantity of heat energy given to the system is equal to the change in internal energy plus the amount of work done. The quantity of heat energy given to the system is equal to the summation of change in internal energy and the amount of external work done. Here, del Q, quantity of heat, du, change in internal energy. Del W, that is work done, which is equal to pressure into change in volume. Now the above equation 1 becomes del Q equal to du plus PdV. Then du is equal to del Q minus PdV. For an isochoric process, volume remains constant. Simply we can write in an rather than or in an isochoric process, volume remains constant. That is dV equal to 0. Change in volume is equal to 0. Now du equal to delta Q. The heat content of a system at a constant volume is called its internal energy. This is a definition for internal energy. Heat content of a system at a constant volume is called its internal energy. See here, this is first law of energy, thermodynamics. According to the definition, the change in internal energy equal to quantity of heat energy given minus work done. If the process is isochoric, volume remains constant. Therefore, the change in volume is equal to 0. Then work done is also 0. PdV is equal to 0. Now du equal to delta Q. It gives a conclusion. The heat content of a system at a constant volume is called its internal energy. In an adiabatic process, del Q equal to 0. In the case of adiabatic process, no heat energy is given to the system or taken away from the system, since the walls of the container are non-conducting in nature. In an adiabatic process, del Q equal to 0. Now this equation becomes du equal to minus PdV. Say this is equation 2. If you put del Q equal to 0 in equation 2, then du equal to minus PdV. This is minus del W. Now we may write del W equal to minus du. In an adiabatic process, the system does work by decreasing its internal energy. This is a valid point. Then only we can call this function as a thermodynamic potential. If the process is adiabatic, work done is possible only by decreasing its internal energy. For an adiabatic isochoric process, du equal to 0. We know that du equal to del Q minus PdV. For an adiabatic process, adiabatic means del Q equal to 0. Isochoric, dV equal to 0. Therefore, du equal to 0. For an adiabatic isochoric process, d equal to 0. That is, the change in internal energy is 0. This gives U as a constant. Now the conclusion is, in an adiabatic isochoric process, the internal energy remains constant. It's all about the term internal energy.